This is a supplemental video for our work on instantaneous similarity-based visual analysis of blood flow in stenosis. You can see I have imported a model of a carotid bifurcation that has a stenosis in the internal carotid artery, which is a high risk factor for stroke. We now want to get hemodynamic information on the artery that shows us the properties of the internal blood flow. However, we do not have flow information for this particular vessel available. Our analysis framework now matches the new carotid model against a database of pre-computed flow models. It finds a neighborhood of similar cases for which we have flow information available. The matches are presented here. They are already sorted, with the first case being the most similar case, the next one being the second similar, and so on. The bar charts show how similar the case is regarding the shape, the diameter, and the stenosis degree. If I'm not interested in a specific similarity metric, I can also disable it here, which instantly resorts the neighborhood and gives me the closest matches regarding the chosen metrics. If I click on any of the cases, it shows the corresponding 3D model with flow information. I can choose one case for comparison, or I can choose as many as I'd like. They are automatically aligned and labeled. When I explore the neighborhood for matching cases, I can make use of the vessel map. Here I can already make out models with, for example, high wall shear stress. If I zoom in, I can see more details on the individual maps, and if I zoom out, I can view many potential comparison cases at once. To now explore the flow features, it is helpful to enable the linked view, which synchronizes the orientation of all vessels, so I can just rotate one and then the other vessels will follow. Let us look at two matches in more detail. The system enables the exploration of multiple flow parameters, the wall shear stress, the reverse flow rate, and also the flow velocity. For each, the peak systolic or the mid-diastolic time step can be chosen. The color map is automatically applied to all models, and I can also change it or change the color map range as required. Note that the color map is also seamlessly applied to all depicted vessel maps. When I select the velocity, the flow rendering switches from a surface display to a streamline rendering to show the internal blood flow. I can immediately see high and low velocity regions and examine if turbulent vortices are present. To get an accurate reading, I can use the integrated probe lens. When I right-click, I can drag the probe over the vessel, which filters the regional streamlines and extracts the maximal velocity within the selection. I can directly compare the probe in multiple models and change the radius. I will now show you a quick demonstration of the whole system, including the extraction pipeline. I can import a new diagram series, which will create a new case and provide me with an overview of the image volume. And then I can crop the carotid bifurcation from the volume. And then in the segmentation module, I get a prediction of the lumen and plug labels. The mask can also be corrected if necessary. For the resulting model, we need to compute a centerline. For this, I tell the system where the tree root and endpoints should be positioned, and then the centerline is solved automatically, and that's all. I can now go into the comparison module where matching flow models are instantly provided. If the database contains geometries that are very close regarding their shape, diameter, profile, and stenosis degree, we found that the hemodynamic simulation of each individual case can be substituted with the similarity-based approach. Very often, the relevant flow information can be obtained by looking at a close match. Therefore, to retrieve clinically relevant information, performing a complex hemodynamic simulation for each new instance may be redundant. We hope that the insights gathered in this work will aid efforts to make blood flow simulations a feasible option for medical applications.